Welcome to another podcast. In this episode, we're going to be taking a look at a sort of a theoretical example. We're going to be looking, there's not going to be many numbers in this example. We're just going to look sort of notationally what is the eigenvalue method. It will have helped if you've watched the eigenvalue and eigenvectors video or if you know what those concepts are, because I'm not going to take the time to go over what each of those are in this video. But I just want to give sort of a high-up view of what we're doing when we do this topic. Almost everything in this chapter revolves around us figuring out what is the solution of a first-order system. And so this is a first-order system. Now, you may not recognize it in this form. So suppose that x has the vector components, x1, which are a function of t, and x2, which is also a function of t. Then, sort of piecing out what I'm looking at here, it would be something that looks like the following. I would have x1, x2 prime, so this vector is equal to some matrix A. Now, I'm going to look at a first-order system of two variables, so we're going to be having a 2 by 2 matrix here. So suppose the matrix A consisted of A, B, C, and D, and then times the vector x once again. And what I want to do is I want to solve this for the values x1 and x2, which means that I'm solving for x. Now, this is the goal of this entire chapter. The only difference is we're not going to change the fact that these are first-order systems, so we're always going to have a first derivative here. The only thing that might change is we might have multiple variables. So we might have more than just x1 and x2. It might be a 3 by 3 system or a 4 by 4 system, etc. But it's basically going to be this problem over and over again for the rest of the semester, in different contexts and different forms. This is the homogeneous version. We'll also talk about the inhomogeneous version. But the point is, we need to be able to solve this. And in order to solve this, I kind of want to think about stuff we did at the beginning of the semester, that what if these aren't vectors? So think about the non-matrix version of this equation. Well, the non-matrix version is x prime equals a times x. So if that isn't a vector and that's just a function x, then solving for x is as simple as doing separation of variables here, or this is one that occurs so often you should know the answer. The answer to this is x is equal to e to the at. Now it would be times some sort of constant, so let me go ahead and put that in here. So it's times some sort of constant. But that's pretty easy to do. And what we wonder is, if the same thing works for the system. And that's what we're going to try in this video. We're going to try to do the exact same solution for the system. What I mean by that is if we have the system version of this instead, is it still the case? So this is sort of a question mark to us. Is it still the case that x is e to the at, where a is now a matrix, times c, where c is a vector? So that's the question that we have, and the answer is mostly yes, but we're not ready to do e to a matrix instead. So why don't we try this? Why don't we try, so our trial solution here is, why don't we try to replace a with a constant? So think about what I just said there. I'm looking for a constant that acts like a matrix. Well, that's an eigenvalue. That's what we just got through talking about in the eigenvalue video. Eigenvalues behave like matrices when they're multiplied by eigenvectors. And so the idea here is my trial solution is going to be an e to the lambda t times a vector, and the vector it needs to be is the eigenvector. So this is going to be an eigenvector, and this is going to be an eigenvalue. That's preliminarily what we think about this. Now, why does it turn out to be true? Well, if I substitute this, so I'm going to substitute into our system. So if I substitute this into our system, then what I'm looking at is I'm going to take the derivative first. So the derivative of this would be, the way that this works is the derivative with respect to t. And so alpha has constants in it, so I can treat this just like a constant. So what is e to the lambda t? Well, it's lambda e to the lambda t. So what you would end up with here is lambda, and then just for the sake of what we're doing here, I'm going to let alpha have components. So alpha is going to have components a1 and a2. So this would be lambda times a1, a2, e to the lambda t. So remember that this is alpha. So you just get the constant lambda times x. That's what you get when you take the derivative. So this represents the derivative of x, and I'm going to set it equal to, if you look at the formula, it's a times x. So a, I'm going to make the 2 by 2 matrix, and then x is a1, a2. That's my alpha in this case. Oh, sorry, excuse me. X is, where's x? X is right here. So x is, alpha is a1, a2, e to the lambda t. Now, because e to the lambda t is not a matrix, it doesn't matter if alpha goes in front of this or behind it. E to the lambda t is just a function. It's not a matrix. So it is commutative with alpha. All right, so this is x, and this is a. So I've just substituted into the equation x prime equals ax, where x is this vector solution involving eigenvalues and eigenvectors. Now, the first thing that you see here is because there's an e to lambda t on both sides, it's redundant. It can go away. So what we end up with here is lambda times alpha equals a times alpha. This is exactly the equation for eigenvalues and eigenvectors. So in order to do this process, I have to locate eigenvalues and eigenvectors, which means I have to take a minus lambda I, find its determinant, set it equal to 0. That's that characteristic polynomial that we talked about before, this lambda squared minus the trace plus the determinant. I have to set that equal to 0 and solve. And then I solve for each equation. So I'm going to take a minus, take the first eigenvalue that you find. That'll correspond to a first eigenvector. So this will, I'll be able to solve for the first eigenvector that way. And then I'm going to take the second eigenvalue, which would be lambda 2, because this is a second order equation, so we're going to end up with 2 eigenvalues. And I'll use that to solve for alpha 2. And then my solution would be, and so this is the important part here, the solution, once all of this is done, so I kind of go back to what we have here, our solution then, find a good place to write this. Yeah, maybe right here. So our solution then at this point would be the vector equation is going to be equal to, well, I need a fundamental set of solutions here. So what that would look like is I would have a C1 times alpha 1 e to the lambda 1t. So this is the first solution, which we usually call like an x1 here. Well, I don't want to confuse that with the components. So we'll just leave it like that for now. Plus a C2 alpha 2 e to the lambda 2t. And so this is what my solutions would look like. Basically, we would take the alpha 1 that we get from here, plug it in. We would take the alpha 2 that we get from here and plug it in. And then that corresponds to the lambda 1, so this would generate a lambda 1 and a lambda 2. And so we use those then to plug in to here. And so you can see that the eigenvalue method is essentially just assuming that the solution is an exponential, and then in order for it to be a solution involving exponentials, it turns out that the matrix can't change the direction of the vector, which makes it an eigenvector. And so we're basically hunting for eigenvalues and eigenvectors of the coefficient matrix A. So really all that's going to matter here is what is A. If you can tell me what A is, then I'm going to find the lambdas and alphas, the eigenvectors and eigenvalues associated with the matrix A, and that tells me everything I need to know about the system. All right, thank you for watching.